It's a pleasure to be here. I was myself a graduate student here some 15 years ago or so, so it's wonderful to be back. I think I may have even taken a class in this room here. So it feels a bit like coming home. I want to talk about representation theory and number theory and the connection between the two. And I want to start somewhat historically about the idea of groups and symmetry and how it arose in, say, the 19th century. There were two kind of main motivations. One came from the work of Galois, who was thinking about polynomial equations and their symmetries, ways in which you can permute the solutions of a polynomial equation. And if you take one polynomial equation in one variable, you have finitely many solutions, so finitely many symmetries. But if you take all polynomial equations together, you obtain an infinite group of symmetries, which has a topology. And this topology is pro-finite, and in particular, totally disconnected. So that was one source of the study of symmetry. And coming from a completely different perspective, Felix Klein was motivated to try and classify the various notions of geometry that were emerging at the time, going beyond Euclidean geometry, such as hyperbolic or spherical geometry. And his idea was to classify these geometries by considering the symmetries or isometries of such a geometry, which in modern language maybe we're going to call a Riemannian manifold. And if you consider the isometries of a Riemannian manifold, what you see is a group which also has a topology, but this topology is very different. It's a locally connected topology of a Lie group. So those two sources of symmetries and of groups had different origins and produced different looking groups. But in the 20th century, there was a bridge that started emerging between those two different concepts of symmetry. And that came in the theory of automorphic forms, of which the first basic examples were modular forms. Modular forms are certain holomorphic functions defined on the upper half plane of the complex numbers with positive imaginary part, which have, let's see, do I have a red, the top, or no, not the top, on, off. Oh, the red one, there it goes. Amazing, okay. It's the middle, not quite the top. So complex numbers with positive imaginary part. And these are holomorphic functions that have a certain transformation behavior. And in particular, that behavior implies that these functions have a Fourier expansion. And the Fourier coefficients in this Fourier expansion carry interesting arithmetic information, and they can be used to form an L function, which is a generalization of the Riemann zeta function. If we put 1 here, we get Riemann zeta function. And if we put these Fourier coefficient, we get a more general L function associated to a modular form. And in this way, these objects relate to the first kind of symmetry, to symmetries coming from number theory. At the same time, they also relate to the second kind of symmetry, because this H here is one of the geometries that Klein was studying. It is a model for hyperbolic geometry. And if we take its group of isometries, or at least the orientation preserving isometries, we get one of these groups that Klein was studying, a Lie group, the group of 2 by 2 matrices with determinant 1 and real coefficients. And we can do a slight manipulation of this modular form and think of it as a function on this Lie group. And the transformation behavior now is going to imply that this function is invariant on the left by a certain subgroup, a discrete subgroup, which can be taken to be the group SO2Z of 2 by 2 matrices with integer coefficients and determinant 1, or more generally, a certain subgroup of that called the level subgroup. And the most interesting of these modular forms, the so-called cusp forms, are not just functions on this quotient, but they're in fact square integrable functions. There is a natural measure on this quotient, but with respect to which these functions are square integrable. And now this puts us in a very pleasant situation, because we have identified these modular forms as vectors in a vector space on which the group SO2R acts. So this is a representation of this group. And not just any representation, it carries a scalar product just by the usual integral scalar product, which is invariant under the group. So this is what is called the unitary representation. And the utility of that is that representation theory gives us a lot of tools to study such objects, and we can now apply these tools to study modular forms. So we see modular form has this large group of symmetries, but in fact, they have even more symmetries that have to do with these Fourier coefficients. These symmetries come in the form of Heck operators, and they're defined in a way that seems to be removed from the action of this group. But in fact, there is a shift of language you can perform so that you can recognize the symmetries coming from Heck operators in the same way as the symmetries coming from this group. And this is the so-called p-adic language, where instead of where we can recognize this quotient as a quotient of a much larger group, now quotiented on both sides. And what is this larger group? This group is the 2x2 matrices with determinant 1, but now with coefficients in the ring of Adels. The ring of Adels being the product of the real numbers, but also all the p-adic numbers for each prime p. So it's a much, much larger ring, which makes this into a much, much larger group. If you're a number theorist, you've likely encountered the p-adic numbers. If you're not a number theorist, you may have not encountered the p-adic numbers. So here is just a very bird's eye view of how you may think of them. The real numbers are a field, but they carry a topology, and the field operations respect this topology. And the same is true for the p-adic numbers. The topology of the real numbers is locally compact, which means that every point has a compact neighborhood. And this is very useful when you want to do analysis, such as you want to define integration. And the same is true for the p-adic numbers. But whereas the real numbers have a locally connected topology, just like the groups that Klein was studying, the p-adic numbers have a totally disconnected topology, just like the groups that Gallo was studying. And I want to give you just a little bit more information. Before we go there, what has now happened is that we have recognized these same elements now as living in a vector space, which has this much larger group of symmetries, where the group SO2R acts as before, but we also have the group SO2QP for each prime P. So a much, much larger group, many more symmetries. And these new factors now encode the Heck operators, more or less. There is some fudging between SO2 and GO2 that I don't want to get into, but in principle, we have revealed many more symmetries, and we have a representation of a larger group that we can study more effectively. Now, a little bit more about the p-adic numbers. What do the p-adic numbers actually look like? If you look from very far away, let's take p equals 3. The p-adic numbers are a set with 3 elements, 0, 1, and 2. The 3 remainders of division by 3. And if you take just one step closer, you realize those 3 elements are just actually themselves sets of 3 elements each. And if you, in this way, you get all the remainders of division by 9. And take one step closer, you realize those 9 elements, each is a set with 3 elements. And now you have all the remainders of division by 27. And now you can imagine you take more and more steps, you get deeper and deeper, and you get a picture that looks like a fractal. You get a picture that looks a little bit like this. And so the p-adic numbers are going to be kind of leaves in this infinite spreading tree. And if you're artistically inclined, you may try to encode them by such picture diagrams, where you have three different colors for the 3 remainders modulo 3, and you start mixing the colors as you're going out into the leaves. But coming back to where this leaves us, now that we have recognized modular forms, which are objects of arithmetic interest, as representations of certain groups, we are led to the following questions. The first question is, try to classify all the irreducible representations of such groups. The irreducible representations you can think of as atoms that are going to form together more larger representations. And here I'm looking at the p-adic numbers for p equals 2, 3, 5, or any prime number. Or if I take the symbol infinity, I'm thinking of the real numbers. So classify all the irreducible representations of p-adic or real Lie groups. The second question is, now let's consider square integrable functions, but just on a single such group, g of r or g of qp. Here, the group acts on the left and on the right. So this is really a representation of two copies of that group, and we want to decompose this representation into irreducibles, into the atomic particles. And then finally, consider the space where the modular forms live, namely the quotient of the adelic points modulo the rational points, and decompose this as a representation of the adelic points of that group. Once we have done this, we can hopefully start addressing the connection to number theory, which Langlands did as follows. Langlands was able to define an L function to any irreducible representation of this L2 space, which is, we can imagine such a representation being spanned by a modular form. And so then the L function will be the L function we just saw in the previous slide associated to a modular form. But this can now be done not just in the setting of modular forms where the group is SL2, but for any reductive group. For example, maybe SL2 can be replaced by SLN or PGLN, or maybe the situation you're studying has some linear algebraic structure on it, like alternating or symmetric pairing that is preserved, and then you'd be looking at the symplectic or orthogonal group. This is how we move from the setting of modular forms to more general automorphic forms. And so Langlands was able to define such an L function. How? Well, such a representation, because it's a representation of the group G of A, and G of A is basically the product of all the GQVs for all the Vs. Such a representation factors itself as a product, and Langlands was able to associate to each such atomic particle, which is an answer to this first question, what is called an Euler factor, something that for Riemann zeta function will be 1 over 1 to the p to the minus s. That's the Euler product expansion of the zeta function. Langlands generalized this to this context, and then the product of these Euler factors gave him this L function. And then he conjectured that all the L functions that arise in number theory are in fact special cases of these L functions. And while this is kind of a general philosophy, it is very powerful because it allows you to study these L functions using the techniques of analysis and representation theory, whereas in their original definition from your number theoretic context, maybe such techniques were not visible. More precisely, this is what Langlands conjectured, that to each such answer of question 1, to each irreducible representation of GQV, one should be able to associate a representation of the Galois group of that QV, and a little bit more precisely, a representation of something closely related to the Galois group called the Wedelin group, and a representation which reflects the linear algebraic structure that the group G carries. If maybe there is a symplectic or orthogonal pairing which comes with this group, and that pairing should be preserved, or a related pairing should be preserved by this Galois representation. But there should be even a second piece, something that commutes with this first piece, and which is important in this global context of automorphic forms, as I'm going to explain in a moment. And then in the global context, when there is an irreducible automorphic representation, which means a representation of G of A that occurs in this space of square integrable functions, there should be associated a representation of the Galois group in such a way that the L function of the automorphic representation defined by Langlands should match the L function of the Galois representation as was defined earlier by Artin. And moreover, the multiplicity of this automorphic representation in the L2 spectrum, so such a irreducible representation could occur multiple times in here, or maybe it doesn't occur at all. That's also a question. Does it occur? And if it does, how many times? This should be computable in terms of this second piece of information, namely, if we take the tensor product over all V of these rows, we get some representation, and then we're asking how often does the trivial representation go in there. So these are Langlands' conjectures. And now I want to explain a little bit about, I'll start explaining about results towards these conjectures, starting with classical results in the 20th century. So the first batch of results go back to Langlands and Harishchandra, and they were trying to classify the irreducible representations of G of QV. So this was question number 1 on the previous slide. So what they did is, first of all, Langlands showed that arbitrary irreducible representation, which, well, there is the technical notion of admissible that maybe I'll ignore here, are related to what are called tempered representations, which is a certain subclass that have nice analytic properties, by a process called parabolic induction. So there are certain smaller subgroups called parabolic subgroups. And if you look at only the tempered representations there and apply induction, you get what? Hello? Somebody is dissatisfied with my presentation. Then you obtain all the irreducible representations of G. This is the so-called Langlands classification. And then you say, okay, that's fine. What are the tempered ones? Well, Harishchandra reduced the classification of those, again, with the same two parabolic induction, to what are called discrete series representations. And if you want to think of the irreducible representations of this group as the atoms that form together complicated automorphic representations, then you can think of the discrete series representations as the elementary particles that form the atoms by this reduction procedure. And a large part of this talk will be devoted to discussing the classification of these. Before we go there, I want to discuss the second question, that of decomposing the space of square integrable functions of GQV. There are two classical precursors of this. One is if you have had a class on representation theory of finite groups, or maybe compact topological groups, you're probably familiar with the theorem of Peter and Weil, which says that if you have a compact group and look at its square integrable functions, that decomposes under the left and right translation of the group into the direct sum over all irreducible representations of pi tensor its dual, where the left action of k acts on pi and the right action acts on pi dual. And if you're more interested in analysis, then you're certainly familiar with Fourier theory. And Fourier analysis tells you that you can write a square integrable function on the real numbers as the integral of its Fourier transform. Well, technically, this is true on the Knowles for Schwarz functions, and then you have to extend it, but let's ignore these details. This identity is still formally correct and explains this Hilbert space L2 of R as a direct integral of one-dimensional spaces indexed by the unitary characters of R. And here, left and right translation are the same because R is commutative. And Harishchandra was able to beautifully generalize both of these theorems into what is called the Plancherel formula, where he said that the square integrable functions on the group G of R or G of QP are the direct integral of pi tensor pi dual, again, the left copy acting on pi, the right copy acting on pi dual, with respect to a certain measure called the Plancherel measure. The integral is initially over all unitary representations, just like it was here. Any irreducible representation of a compact group is automatically unitary and finite dimensional even. And here we have taken specifically the unitary characters. But it turns out that the Plancherel measure is supported only on the subspace of tempered representations. Those are the ones that showed up here. And not only that, but Harishchandra was able to explicitly identify the measure with respect to which this direct integral is taken. And this measure contains quantities related to the construction of tempered representations in this bullet point 2. So a tempered representation occurs in the parabolic induction of a discrete series representation. Here's the parabolic induction of a discrete series representation. And the Plancherel measure basically takes what is called the formal degree of the discrete series representation, which is a stand-in for the dimension. Even though this representation is infinite dimensional, there is some kind of formal analog of dimension called the formal degree. And then there is the famous Harishchandra mu function, which maybe I'll not say much about at the moment. The point being that there is an explicit and not too complicated formula for the Plancherel measure. And something interesting is happening. All of these results hold uniformly for p-adic numbers and real numbers. And this prompted Harishchandra to formulate a philosophical principle called the Lefschetz principle, which postulates that the representation theory of real and p-adic Lie groups ought to behave in the same way, which is quite provocative if you think about the fact that real and p-adic Lie groups have very different topological structure. On the one side, you have this locally connected topology. On the other side, you have this totally disconnected topology. So as topological group, they look very different. And from the beginning, there is really no reason to expect that their representations should behave in a similar way. And yet those initial results going down to discrete series, which we'll talk about in a moment, are uniform for those groups. And so this is what motivates Harishchandra to formulate this principle. Now let's talk about discrete series. Before we go there, I've created here a little picture to explain to you the tempered representations, to give you an example for the simplest group, namely SO2R. So what you see here are two kinds of families of representations. Horizontally, you see a family of discrete dots, one for each integer, if you will. And these dots become bigger and bigger and bigger as the integer grows. This size reflects the formal degree that I mentioned in the previous slides, this stand-in for the dimension. These representations get higher and higher dimensional in certain sense. And that's the discrete series. And you see why it's called discrete series. It's because it's discrete. And then you have tempered representations that come in a continuous family. There are two such families, which are these two vertical lines. One is just a real line sitting vertically. And the second one is a real line, except that the origin is doubled. There are two dots in the origin because there is a certain reducibility there. But this is roughly what the picture looks like. Now let's discuss the discrete series. This is again something that Harishchandra did, but now only over the real numbers. So here we start diverging from the Lefschetz principle, and progress was made over the real numbers. Harishchandra classified the discrete series of real reductive groups by triples, where the first part is what is called an elliptic maximal torus, but this is just lingo that basically means a subgroup of the real Lie group, which is abelian and compact and maximal with these properties. And then a character of that subgroup. And then also this third thing, B, is a certain cone in the character group, which comes from Lie theory, from the theory of roots. And this cone has to contain the character. But now in most situations, this character only sits in a single cone and determines the cone. And for those, which we may call regular, it's really just a pair of a compact subgroup and a character on it that is regular. What does this look like for SO2R? Where in the picture previously, we saw that on SO2R, we have discrete family of dots that grow bigger and bigger. How does this connect to this presentation here? Well, in the case of SO2R, this compact torus is just the unit circle in the complex numbers. And what are the characters of the unit circle? They're just powers by integers. Those are the only continuous characters of this group. And there are two cones, two choices of B, namely the non-negative and the non-positive integers. And so you see that such a character, unless it's the trivial character, it sits in exactly one of those cones. It's either a positive or a negative integer. Only the trivial character sits in both cones because it's both non-positive and non-negative. And so the sequence you're seeing is that negative integers that sit in a negative cone, then the integer 0 sitting in both cones, and then positive integers determining the positive cone. And this is exactly the picture of dots that we saw in the previous slide going out to both directions. And how does this connect to modular forms? Well, the integers in the positive cone correspond to holomorphic cusp form of weight k plus 2. And in addition, Harishchandra, after classifying the discrete series representation, also gave a formula for their character. If you're familiar with representation theory, you know that the character of a representation is an important invariant that actually determines the representation. And the way it's defined for finite dimensional representations is to take the trace of a group element acting on the representation. Now, these representations are all infinite dimensional. So taking the trace of something on an infinite dimensional vector space doesn't work. And yet Harish-Chandra had an ingenious way to make it work and to create a function which behaves exactly like taking the trace. And he gave a formula for it. And this is what the formula looks like. I won't go through the bits and pieces now, but I just want to emphasize one qualitative nature of it. It's a sum over elements of the Weyl group, up to some plus minus constant here. And you take the character, which classifies the representation, and you put the element where you're identifying this trace function at the various Weyl translates of this element, and then there's some denominator. So if you're familiar with the Weyl character formula from the theory of algebraic groups, you'll notice that this formula is very, very similar to that, except that here you're taking only the real part of the Weyl group. Now, what about p-adic groups? Now we're coming into the 21st century because progress on this problem was much slower than for real groups. P-adic groups turned out to be quite a bit more complicated. First of all, there are results from the turn of the century in the work of Moy and Prasad, who really leaned into the they went away from the Lefschetz principle and they wanted to explore the way in which p-adic groups are different from real groups and the fact that their topology is totally disconnected. So this was reflected in Moy and Prasad defining certain filtration towers in those totally disconnected groups by compact open subgroups that converge to the identity element. And using those, they were able to define a notion of depth of a representation. Namely, how far in this filtration do you have to go before you meet vectors that are fixed by this filtration subgroup? And then they were able to classify all those supercuspidal representation, which is supercuspidal is a strengthening of notion of discrete series. And this is what I'll be talking about as far as classification is concerned. All those which are of depth 0. And Moy and Prasad showed that they come via a process called compact induction, which is not very dissimilar from parabolic induction, from cuspidal representations of reductive groups over finite fields, which is something that George Lustig had studied for many decades prior. And so if you accept Lustig's work, which comes close to giving a classification of these representations, but you have to accept Lustig's work for possibly disconnected groups over finite fields, because this is what relates to p-adic groups, then Moy-Prasad theory provides a classification of depth 0 supercuspidal representations. Going beyond depth 0, there was a construction by Jeff Adler, generalized by JKU around the turn of the century, which produced supercuspidal representations of arbitrary depth out of complicated input data, which looks like this. I won't explain all the pieces, but basically you have a whole tower of subgroups and a whole sequence of representations of them, the first one being of depth 0, so connecting to the previous theory. And out of this, by some black magic, there was a construction of representations. Now, a construction is very different from classification. And so how do you go from construction to classification? The first question is to wonder, does this construction produce all representations, or maybe some of them? That's the question of exhaustion, which was studied by Julie Kim and by Jessica Finsen, the second result being just a few years old. And they proved, and this is Finsen's stronger formulation, that if P does not divide the order of the Weyl group, then yes, use construction produces all supercuspidal representations of arbitrary depth. Very good. So we're getting closer to classification. But now the second question is, can it happen that different such input data produce the same representation? The answer is yes. This was studied by Hakim and Murnahan, who gave an explicit equivalence relation on such data that described exactly the fibers of this map. And so now we have something that comes close to a classification of these representations, but it's a classification by complicated data up to complicated equivalence relation. And then we think back to the Lefschetz principle of Harish-Chandra and the fact that he classified discrete series of real groups in such simple terms, just a torus and a character. And here you have this complicated data by complicated equivalence relation. And then you wonder, does the Lefschetz principle fail now that we are really down at the grainy level of elementary particles? and we start seeing that these groups really are not the same kind of groups? Or is there a way to restore the validity of the Lefschetz principle? I should also say there was actually some drama in this whole business, which is after 20 years of using use construction in many papers, it was discovered that there was an error in the paper review. And then all the people who had written papers based on use construction got very cold feet because it wasn't clear if their papers was worth anything. And the error is actually kind of interesting. So you was quoting a paper of Girardin from the 70s. And there is a statement in Girardin's paper from the 70s about the character of the Weil representation. And that lemma was a wrong lemma with a correct proof. So what happened was, if you look at the proof, all the arguments are correct, and at the end you have the correct conclusion, but that conclusion doesn't match the statement of the lemma. And it's not clear how this happened. Maybe it was in the time where secretaries were typing up manuscripts and the secretary forgot to include an important term from that formula. And JKU dutifully quoted the lemma and had a correct argument based on an incorrect statement, which had a correct proof. So now everybody had done their job correctly except for one little mishap, but in the end, things were up in the air. And so it turns out that one can repair use construction. Finsen had a repair by basically replacing half of use papers with different arguments. But then I wrote a paper with Finsen and Spice where we had a different approach. Instead, we changed the construction to make use arguments that had become invalid valid again, which was important because those technical results of U ended up being useful beyond his own paper. They're useful in computing the character, which we're going to talk about in the next slide. But modulo this drama, now we have this classification and we're wondering about the Lefschetz principle. Now, when we were talking about the construction of the classification of discrete series by Harish-Chandra, there is this concept of regular discrete series where instead of triples, we had pairs. And so why not also think about a regular supercuspidal representation? What that would mean is that it's a supercuspidal representation where in use construction, and maybe I'll remind you, there was this depth zero piece here, which is related to Lustig's work. And Lustig had a notion of regular representation over a finite field. So we're going to call a supercuspidal representation regular if this depth zero piece in the construction itself is sufficiently regular in Lustig sense. And then in two papers of mine, one was published some time ago and one is still languishing in one poor referee's desk. I was able to show that in fact, the regular supercuspidal representations are parameterized exactly the same way as the regular discrete series by a pair of an elliptic torus and a regular character of that. Except that in p-adic groups, there are many, many more elliptic tori than in real groups, which is where the complication kind of hides behind the statement. And then the slightly more general case of semi-simple supercuspidal representations is classified in a similar way, just by a triple with another piece. Maybe I don't want to go into those details. And then there is the question of the character formula. This has been worked on in over the last almost 20 years by various authors, Adler, DeBacker, Spice in various permutations. And then in my paper with Finsen and Spice, we end up with the following formula, which if you look at it qualitatively, it looks very much like the formula of Harish-Chandra. There are some constants in front. There is a sum over the Weil group. And there the Weil translates of the element fed into the character that produces the representation. And not only is this structurally similar, but in fact, all of these bits and pieces make sense of the real numbers, and there you recover precisely Harish-Chandra's formula. So in other words, now we have the Lefschetz principle restored among the discrete series, both in terms of classifying the representations and in terms of understanding the character of these representations. There's a uniform formula for the character, at least for elements of that torus in the real and in the p-adic case. Now let's go back and connect to Langlands' ideas now that we have understood something about classifying the representations. we want to relate them to the number theoretic sides and the Galois group. The basic form of Langlands' conjecture is to assign to every representation, irreducible representation of G, some representation of the Galois group, which we formulated in this way. And many properties are required of this assignment, but none of these properties really gives a unique characterization of this assignment. And so we are shooting for something that we don't quite know exactly what it is. But nonetheless, that didn't prevent people from making constructions. Langlands made a construction for all real groups. For p-adic groups, the progress was much slower. And Laurent, Rappaport, and Stuhler were able to treat the group GLN, n by n invertible matrices, over local function fields in '93. And then in a famous theorem from 2001, Harris and Taylor, and then NER shortly thereafter, were treated the same group over the p-adic numbers. And then for a while, things stalled, but one can try and do something a little bit weaker. There is a notion of a semi-simplified representation, where instead of taking the full Weil-Deligne group, one just takes the Weil group and restricts the representation to that. The full Weil-Deligne group contains the Weil group and also a certain unipotent element, which is why restricting to the Weil group is called semi-simplification. And here there is work of Genestier and Laporte from a few years ago, where they constructed this semi-simplified correspondence for arbitrary groups over local function fields. And then very famous work of Farg and Schulze from just a few years ago, where they did the same over p-adic numbers. We can go in a different route, and instead of asking about semi-simplifying, we can ask about having this full representation, but also enhancing it by this datum rho that I mentioned a few slides ago that was important in the global context. And this leads to the refined local Langlands conjecture, which is required for many applications, especially global applications, such as the automorphic multiplicity formula. And there, what we want is an actual bijective map, which can be seen as a different form of classifying these representations, where in addition to the Galois representation, we have the second commuting datum rho that was important for the automorphic multiplicity formula. It was recognized by David Vaughan that such a thing is not quite right if you only use a single group. You have to treat multiple groups together, which are called inner forms, and you have to do it in a cohomologically correct way, which is called rigidification, where you have to replace the cohomology of the Galois group by cohomology of more complicated objects called Galois gerbs. The right object over the real numbers was identified in work of Adams, Barbash, and Vaughan, and then work of mine and a student of mine showed what to do over p-adic numbers and then local function fields. And having that in place, the basic conjecture is that there should be a bijection of this kind, but you need to take all the inner forms and you need to treat them appropriately with respect to this rigidification. Then there should be a bijection of this sort. And there should be certain normalized character identities that tie it with the Arthur-Selbach trace formula. And the upshot of that is that if you consider an automorphic representation over a global field such as the rational numbers, the multiplicity of this representation in the automorphic spectrum should be measured by the multiplicity of the trivial representation in the tensor product of these enhancing objects here. This is something I mentioned a few slides ago in a maybe less precision. So this is the rough shape of conjectures. Now, what is known about these conjectures? First of all, Langlands and Schellstadt again proved most, if not all, of these statements already in the 70s and 80s over R. And over QP, again, progress was slower. Arthur, in a celebrated book now about 10 years ago, treated quasi-split symplectic and orthogonal groups, but also proved the automorphic multiplicity formula. So his work was both local and global. His student Bin Shu extended his work to similitude groups, but proved somewhat weaker results. and then Mock in 2015 translated Arthur's work to quasi-split unitary groups, and a joint work of myself with Mingus, Shin, and White treated non-quasi-split unitary groups. And the specific case of the similitude symplectic group with 4 letters was treated in much greater detail than Bin-Shu did by Gan, Takeda, and Chan. But now there is somewhat of, again, drama in the subject, which is that there are exclamation marks among many of these results. And I'm going to go into these exclamation marks, but basically they mean that there is a problem with the validity of these results that is slowly becoming more and more common knowledge in the field. And I'll devote a few slides to discussing what the problem is, including, of course, my own work here is afflicted by the same disease as those other works. But there is another approach you can take. Instead of thinking of specific groups and handling all representations, you can try to handle all groups, but only specific representations. And the specific representations I'll be thinking of are on the Galois side, discrete Galois parameters, which you can think of irreducible Galois representations, basically, large enough, and also semi-simple. And in that case, in the same paper that's collecting dust somewhere, I was able to construct this correspondence for pretty much all reductive groups, at least those that split over a tame extension, where the prime does not divide the order of the Weyl group. This is the same restriction as in Vincent's result. And also in my work with Vincent and Spice, we proved the normalized character identities under even more conditions on the base field. Before I go into the global situation, I want to revisit the local situation a little bit and go back to discrete series over R and work on Adams and Vaughan from the 90s that elaborated a little bit on Harish-Chandra's classification that I mentioned earlier. So let me remind you, Harish-Chandra classified discrete series by such triples, and he gave a character formula of this shape. Now, we can make a very simple algebraic manipulation to this character formula and write it in a more symmetric way like this. This is, if you've taken a course on Lie algebras, you've seen this. This is the famous Weyl denominator. And it's a little bit different from this one here. And the difference is that it is more symmetric, both in terms of optics, but also in terms of the action of the Weyl group. When the Weyl group acts, this changes by a well-determined sign. And then we can take this piece and shove it up there, and this is the formula we get. But see what happens now is that in the classification that used to be triples, now it just became pairs, because this modified character is always regular, and it always determines the cone. So this simple manipulation made the classification a little bit nicer, and also made the formula a little bit more symmetric. But there is a price to pay, which is now numerator and denominator are no longer functions on the torus, rather they are genuine functions on a certain double cover of this torus. And then you can wonder, is it really worth it to make the formula look nicer, but introduce this complication? But if you look a little bit closely, you start realizing that this cover is actually something very pleasant. First of all, there is a local Langlands correspondence for this cover. This cover has an L group of its own. Okay, that's not necessarily an advantage. It just puts us in the, at least in the same playing field as the non-cover. But here comes the actual interesting thing. There is a canonical embedding of the L group of this double cover into the L group of G. Whereas beforehand, for the usual torus, there is no such canonical L embedding. And the lack of this canonical L embedding made the construction by Langlands hard to follow. There was a lot of ad hoc machinations of extracting data, wherein if you use the cover, everything streamlines. And this was the point of view of Adams and Vaughan over the real numbers. But it turns out you can do the same thing over any local field. Now, this has the same label here as the other one, but this is a different paper that collects different dust on a probably different referee's desk. And there, what I was able to show is that for any quasi-split connected reductive group, in particular a torus, there is such an, first of all, there is something funny. There is a compact abelian group, which you can think of as a fundamental group of that group. And there is an extension of this kind. And here is a little bit of information about this fundamental group. It's related to the Galois cohomology of the center of the dual group. And moreover, anytime there is a refined local Langlands correspondence for these covers, there is an L group that you can define for them. And moreover, anytime you have a subgroup of the L group of some reductive group with some very weak properties, that leads to a quasi-split group H and a cover of it, such that the L group is canonically isomorphic to this subgroup, which means that if you're familiar a little bit with the concept of Langlands punctoriality, you now realize that Langlands punctoriality is closely related to thinking about these covers. It naturally leads you to thinking about such covers. And this, going back to the idea of Adams and Vaughan, we now get an application of this story, namely, you can uniquely characterize the local Langlands correspondence for discrete semi-simple parameters, which is what I mentioned. You're trying to construct something, but there is no unique characterization for where you're going. Well, now we can give a unique characterization. Namely, if you start with a discrete L parameter, in a canonical procedure without any choices, you obtain, using this result on covers, a torus and a cover of it, and a genuine character, and then you can write a formula for what should be the stable character of the corresponding L packet. And this, by just mere linear independence of characters, uniquely characterizes the L packet that you're supposed to construct. So now you're expecting to have a local Langlands correspondence, but not only that, you know exactly what should come at the end. The only thing you don't know is how to get it, but at least you know what you're shooting for. Okay, so now I want to switch from the local story to the global story and say a little bit about what is known about automorphic forms. I mentioned already the work of Arthur and then Mock's translation and my joint work with these other authors on classical groups, which results in a decomposition of the automorphic spectrum according to what is called Arthur parameters, and also the proof of the Arthur multiplicity formula. And now there comes a problem, which is related to the red exclamation marks a moment ago, which is that Arthur's original work and then everything that depends on it is based on certain papers that are quoted in his more than 600 pages long book. In the bibliography, they're called A25, 26, and 27, and they're listed as papers in preparation. But the book was published over 10 years ago, and the papers were never prepared. There are multiple statements that are punted to these unprepared papers. Let me mention the most important in them. One is called the so-called non-temperate intertwining relation, and the other one is the study of the disconnected group O2N. And I'll spend just a few minutes talking about each of those. But the problem is, this makes all the results in these works conditional on these gaps. Why are they conditional? Because the argument in these results is a huge induction on the dimension of the group, which starts in the beginning of the book and ends at the end of the book. So it's a huge induction step. And if in this induction step you're missing a piece, then the whole induction falls apart and you have nothing. And so there is work in progress currently. One is joint work with Hirako Atobe, Wei-Tech Gan, Atsushi Ichino, myself, Roberto Mingus, and Seok-Woo Shin, in which we're proving this non-temperate intertwining relation for classical groups. And we're quite confident now that we can do it. We met just 2 weeks ago, and we had some progress. So now I'm happy to feel more optimistic about it. Another is a preprint of mine, which is already available, which formulates the Langlands conjectures, at least in the local case, for disconnected groups. In particular, in this case, this is just formulating conjectures. But then there is ongoing work of myself and Paul Mezzo, where we prove these conjectures for real disconnected groups, including the real group O2N. Now, let me say Actually, I have no idea what time it is because I have no clock, so I don't know where I stand in terms of time. I have a few more minutes. About 10 minutes. Okay, good. So let me say a few words about the non-tempered intertwining relation and a few words about the disconnected groups. So the non-tempered in the general the intertwining relation, I'll present it with three questions: why, what, and how. Now, why is the intertwining relation an important thing? Well, Arthur's argument involves the so-called Arthur-Selberg trace formula, which is a certain distribution that studies this L2 automorphic discrete spectrum and the trace of test functions acting on it. And since this is where automorphic forms live, this is the information that you want to get. The trouble with the trace formula is that it doesn't just give you this, it comes packaged together with information that you maybe don't care too much about coming from Eisenstein series. And in order to get the information you want, you need to peel off the information that you don't want. And one of the main tools that Arthur uses is the so-called stabilization of the trace formula, which is writing the trace formula as a sum of so-called stabilized distributions, stabilized trace formulas over endoscopic groups. And the intertwining relation is precisely the object that relates the Eisenstein contribution that you want to peel off to the stabilized trace formula for smaller groups. And if you're doing induction on dimension, you understand all the smaller groups that allows you to absorb the Eisenstein contribution and uncover the contribution you're interested in. So the intertwining relation plays a key role in this argument, and without it, the whole argument doesn't work. Now, what is the intertwining relation? Well, here it is. It is an identity of two sides. One is the stable character, which is something I gave you a formula for a few slides before in the setting of discrete semi-simple parameter. It's the stable character on the endoscopic side, which is given by the primes. And the other side is part of the Eisenstein spectrum here, namely is the trace of a normalized intertwining operator acting on parabolic induction. So it's a simple enough looking identity, but so was the fundamental lemma, and that doesn't mean that it's easy to prove. Now, this one is not as hard as the fundamental lemma, but it's still quite subtle because you have to relate subtle normalizations of intertwining operators against subtle normalization of endoscopic objects. And but this is the identity, and then our approach to prove it, I'll just give a very, very basic schematic, is to first brute force calculation of very, very special cases. The way these things work is you have a lot of machinery, and you can reduce if you're clever to a certain kernel case, but there is some law of conservation of misery, which is you cannot reduce yourself to nothing. You can reduce yourself to something, but at some point you have to do some very serious work. And it's done here by computing explicitly exactly this identity in cases that you can hopefully control a little bit. So that means computing both the arithmetic part, so there's L and epsilon factors of non-abelian Galois representations that need to be computed here, and compare it against intertwining operators, which are defined by divergent integrals that you have to normalize and then compute. Once you have handled these special cases by hand, there is an inductive procedure to amplify this to what are called good parity anti-tempered parameters. And then there is a globalization argument by spreading out along multiple places to handle all non-tempered parameters. So this is about the intertwining relation. What about disconnected groups? The goal here is to formulate all of Langlands' conjectures to these reductive groups that are not necessarily connected. And the hope is to have a language where you cannot tell if the group is connected or not, that works uniformly, and that allows for normalizations and arbitrary component groups. In particular, it goes beyond twisted endoscopy, which allows just cyclic component groups. And here, the following work is in progress. First of all, I mentioned the preprint that I already have where the local Langlands conjecture and endoscopic transfer is formulated, and normalizations are done. And also there is a proof of these conjectures for tori. Now, tori may seem a little underwhelming, but these are disconnected tori, so they can be non-abelian, they have higher dimensional representations. And so something subtle is going on. You need to match certain extension classes between the automorphic and the Galois side. But with this in mind, this was just the local story. Then there is work of Yi Luo, who was a graduate student of Wei Teg Gan, who formulated and proved the automorphic multiplicity formula again for disconnected tori. So that was the first step in the global program for disconnected groups. And then finally, I mentioned my work in progress with Meso, where we prove these conjectures over the real numbers. This is some input that goes into that work. And this is all I have today.
I'm not sure if this is too technical question, but it's possible to compare the parameterization of reducible representations, that fixed elections principle, a complicated one to do with that chain. Is there a way of seeing the relationship between those two, or would you be able to comment upon that?
Oh, how you get from the input datum for the U construction to this simplified?
Yeah, to your simplified.
Sure. I can say a few words about it. There's two directions really. There is a simple direction in which this depth zero piece, the pi minus 1 piece, that's related to Lustig's work. If you look at what regularity means in Lustig sense, this means that there is a what is called regular Deligne-Lustig induction. So the way the p-adic group and the finite group are related is there is a point in the Bruhat-Titz building, and the Parahori group, then it has an integral model, and the special fiber of this integral model gives you this finite group of Lie type. And there is a torus there, and whose Deligne-Lustig induction will give you this representation there. Now you have to do this in a disconnected setting, so you have to amplify Deligne-Lustig theory to disconnected groups. But then this torus can be lifted integrally, and it gives you a torus in this smallest p-adic group in the chain. And then, and also a character of that torus of depth zero. And then you can take all the other characters, you can restrict them to this torus, you can take the product. And that is this pair of torus and character. Now, this idea was floating in the air already a few years before my work, but what was completely unclear is when you do this, what kinds of objects do you get? What kind of pair of torus and character do you get? And so what I was able to do is reverse this procedure by generalizing work of Roger Howe, who had done something for general linear groups. He had something called the Howe factorization lemma, which tells you that if you start with a degree n extension and what is called an admissible character of it, you can factorize it into a sequence of twist levies and a sequence of characters of those levies, which when you compose with a determinant and take the product, you recover the original thing. So it turns out this can be generalized to arbitrary connected reductive groups. And that gives you an inverse procedure. And now this means that the simple procedure that I just described, you have identified the image of what this is. And this image, you can say exactly what characters are in the image, because you can factorize those back. So that's really what's going on. And then the point is that in this factorization procedure, you're making choices. So you can factorize such a pair in multiple different ways. And then you have to prove that all of these ways are related by what Hakim and Murnaghan called refactorization, which is exactly their equivalence relation on the data that describe the fibers of the map.
Wondering, has Arthur given up on his
maybe that's a question for Jim. I don't want to comment on what his state of mind is. I think he has been meaning to work on them, and probably he still is meaning to work on them, but I cannot speak for him. I have been in contact with him, yes.
Kind of current statements relating Schultz to other constructions.
Right. So There is a number of results on this. There is a result of Linus Hamann for I forget if it's either SP4 or GSP4, one of these, where he links Fark-Schulze to the result of Gunn and Takeda that I mentioned. There is work of Bertoloni Belli and I think I'm going to butcher his name, sorry. Nguyen, Hugh Nguyen, I think I found it, who treat unramified unitary groups in odd many variables. And then there is beautiful work by Daniel Lee Huerta, who relates Fark-Schulze for local function fields to Genestiello-Fork for local function fields and proves that those are the same by basically proving a local global compatibility between the Fark-Schulze work for local function fields and the Laforgue work for global function fields. So those are the things that come off the top of my head. Right.
I mean, I guess people like you have thought about this.
Right. So Michael Harris has been thinking about this, and he has ideas of using L functions in order to be able to kind of whittle things down to. I think his argument works over local function fields where you don't have trace formula, but you pretend you do, and then you have base change. And you want to work with base change in order to put yourself from the, say, supercuspidal case up to a principal series case where you can line things up kind of in a simple way. But this is not fully fleshed out. I think he has done some work with Buzzard-Plessis where they treat a simple situation. But my personal philosophy would be to use this conjecture that I mentioned that uniquely characterizes the correspondence by the formula for the stable character of an L packet and try to see this geometrically on the Fark-Schulze side. And so we have very preliminary work on this. So in my paper with Weinstein and Hansen, we have a geometric way to understand the character on the elliptic set by a certain object called the inertia stack that's associated to that. But this is still very abstract. The path from that to this particular formula is absolutely unclear to me. And I've talked to Weinstein about it a little bit. I mean, I see glimpses. I know, for example, that, so what our idea was to use a Lefschetz fixed point formula to get a handle on this. And I know that this can be done over the real numbers, and you get Harris-Chandra's formula over the real numbers using an index formula, which is similar to the Lefschetz fixed point formula. So one can try to do something in that direction, but it's unclear if the Fark-Schulze geometry is explicit enough at this point to where you, after running the Lefschetz formula, you can actually compute something explicitly out of it. So at the moment, this is still just dreamland, but my hope is that using this character formula, one should be able to relate them.
So how does the stable optimal integral, the jump condition for stable optimal integral fit into the Lefschetz principle?
Yeah, that's a beautiful question. The jump conditions for real groups are related to the germ expansion for p-adic groups. And at the moment, I don't see a way to line them up. I haven't seriously thought about it. I have looked at just the very simple case of p-adic SL2, and there I seem to recognize these same kind of jump-like conditions in the p-adic setting. And when I said this to Jim Arthur, he labeled me a heretic for saying that to him, the germ expansion is what happens on p-adic groups. So I mean, he meant it jokingly, of course. He thought this was an idea people haven't thought about, but of course, the philosophical idea of jump condition doesn't make sense p-adically, because what you need is to have an idea of kind of, you have something connected and continuous so that you can jump. But if your topology is totally disconnected, you're jumping the whole time. So there is no not jumping. So formulating what it means to jump in a totally disconnected topology is a little bit questionable. and I think people haven't seriously thought about it. I've thought about it a little bit, but I don't have anything definitive to say at the moment beyond the fact that the usual way is the germ expansion.